So thanks everyone for joining us today for this memorial lecture for Geert Jan van Oldenborgh in person and mostly online these days. So most people will join us probably remotely. So my name is Philip Stier. I'm the head of atmospheric, oceanic and planetary physics in the Department of Physics, where Geert Jan was also a visiting professor. So Geert Jan started off his career with a master's in theoretical physics from Leiden University. Then did a doctorate in particle physics from the Dutch National Institute for Subatomic Physics, and then moved on to researching elementary particles first at LMU Munich, and then the Paul Scherrer Institute in Switzerland. And then in 1996, he switched careers and joined the Royal Netherlands Meteorological Institute, KNMI, and he worked on topics like El Niño, seasonal forecasting, and climate dynamics. Then he was also one of the co-founders of this field of climate science called climate attribution or event attribution, and which aims to establish the links between extreme weather events and climate change. And we will hear much more about this topic later today by the speakers. But Geert Jan was also a lead author of the IPCC Sixth Assessment Report. He was named by the Time magazine as one of the 100 most influential people of 2021, together with Freddie Etzel, who is also here today. And in 2021, he was also awarded the Knight of the Order of the Netherlands Lion in recognition for his contributions to climate science. But maybe aside of awards, it's really worth mentioning that he was just a fantastic colleague, enthusiastic and inspiring, and full of energy to talk science. He made it, despite his health, he made it to Oxford as much as possible. And when he came here, he really joined the events we organized of the Climate Research Network. And he was one of the late leavers in the pub and still talked science at the end of the evening. So that was great. He also volunteered to give lectures to our graduate students and was an enthusiastic teacher. So this was really fantastic. So we'll miss Geert Jan dearly, but we're really happy to have some of his closest collaborators here today. We'll introduce now. So I'll start with Robert Bouton. He's the director of the Institute Pierre-Simon Laplace and a senior scientist of the French National Center for Scientific Research. He's also coordinating lead author of the IPCC AS6 chapter, the Sixth Assessment Report chapter, focusing on regional impacts and risk assessment. And he works on a wide range of climate topics, but also particularly also the development of climate services, regional climate and energy modeling, and understanding extreme events. And I guess we'll hear more about extremes throughout the lectures today. And I'll right away introduce also the second speaker of today. This will be Friederike Otto, who was here in Oxford when Geert Jan was here, also a visiting scientist, but now she's a senior lecturer in climate science at the Grantham Institute for Climate Change at Imperial College. And her main research interest is becoming a theme, is extreme weather and event attribution. And she focuses on droughts, heat waves, and storms, but then many other related topics. And she also is a lead author of the IPCC AS6 report and a co-leader of the World Weather Attribution project that she co-founded with Geert Jan in 2014. And finally, Miles Allen, our third speaker, is professor of geosystem science in the Environmental Change Institute in geography here in Oxford, but also in the Department of Physics here in Oxford. And his research focuses really on human influence and national influence on climate change. And with a theme, he also started to work quite heavily on event attribution and extreme weather. In fact, he proposed really the underlying theoretical concept of some of this early on in 2003, and then worked on quite a few papers with Geert Jan and really helped to get this field started. So I couldn't think of a much better set of speakers in memory of Geert Jan and to cover his science interests. So without any further delay, I will just head straight over to Robert.
So thank you so much for this invitation. I'm really honored here to be here with you. It's my first travel abroad for work in 2 years. So I'm really happy that it is here actually, and to celebrate my colleague and friend Geert Jan van Oldenborgh, and to tell a few stories, a few scientific stories about what he has done and how this is coming through future science. Now it's been about 4 to 5 months. I can't remember exactly. It was in October. But what I remember for working with Geert Jan was that every single discussion was full of sparkles and was triggering open questions, was triggering papers, projects. And there were so many that there are still ongoing papers that we haven't finished yet. There are some which were kind of in trouble with some reviewers, which we will still finish next year, probably. But it was a fantastic experience to work with Geert Jan. So many questions remain open, and I will give a few of them after recalling what Geert Jan has done a little bit. I will focus on meteorology here, but he's done much more, especially with Freddie, who will talk about other aspects, I guess, in the following lecture. So I think if we look at this very famous now figure from the IPCC report, the 6th IPCC report, which came out in August, which tells basically that climate change is already affecting every region, everywhere, with extremes, especially with heat waves, with lots of confidence. So there's this hexagon representation. We discussed a lot about hexagons in the IPCC. I think Freddie was the initiator of the hexagon stuff. Now it's very fashionable. The hexagon, was a way to show regions without showing boundaries, because otherwise it can be politically sensitive. So that's a nice representation, and it shows the regions of the world where we have confidence in the attribution of extremes. For heat waves on the top, and for extreme precipitation on the bottom left, and droughts in the bottom right. So the confidence goes a little bit down as we go to first precipitation and then droughts. But for heat waves, it's absolutely obvious and demonstrated that we have already a sign of climate change in every single region, almost. So how did we get there? How could we go to this to these conclusions? These were not the conclusions of AR5. So this is new, really. The fact that everywhere we see a signal of climate change. Because some very strong thinkers back in the 70s were already anticipating at the time where the signal was not, there was no signal, basically no signal in the 70s. Some people even said that we could enter a new era of ice age or something like that. There was a few people like that in the 70s, because essentially the aerosols were doing, due to the sulfates, were doing a really bad jobs on the climate, especially in the Northern Hemisphere. But some thinkers like Klaus Hasselmann did actually think that climate change will come, and we have projections, and we need to be prepared by some methods, by designing methods for what we call detection. So we have to be prepared to see where we will find the signals of climate change. So these were detection methods. I'm not going to go in details, of course. And these methods started to be applied in the 90s, with especially the work of Gaby Hegel and other people, and were applied to the attribution of the mean climate change, the mean, the climatologies which was changing. And of course came the 2000s, and some brilliant thinkers before the event, I think, started to say we have to look at single events, and do we see a signal of climate change in single events? And I think, Miles, I think you did your paper before the 2003, or you started your work before the 2003 heat wave. Am I correct?
It was before the heat wave, but it was more important event, which was that our kitchen nearly got flooded.
True, can't be more true. So in any case, that was the start actually of event attribution, because we wanted to know whether single events could have a signal of climate change. So since then there was many studies, and that's exactly where we needed methods. We needed rapid methods. We needed efficient methods to look at, extreme precipitation here, heat waves there, because there were many. And the first one, if I'm right, so I'm not fully sure about if it was the first one, but at least the first almost real-time case was a Thailand case. In 2011, there was a lot of flooding there, and actually Geert Jan at this time concluded that there was no signal of climate change. So it was published. So he was publishing also negative conclusions. So how did he get there? Because essentially he designed a way, with his co-authors, of course, a way to do things in a kind of systematic way and very fast way. You don't need simulations. You have to use, you can use simulations that already exist. And so this is an example of detection with the temperature, the highest temperature in the year in Debuilt, the time series on the left. And if we look at this time series, we can do a lot of statistics with that. There's not so many numbers after all, but we can do a lot of statistics. And in particular, do what we call generalized extreme value fit. So we fit a parametric distribution to the data, but this fit is not the same in the early days as in the later days, because there's obviously a trend. So this fit was taking into account what we call a covariate, which is the global surface temperature. So given this, I'm not going to go in detail, but basically what the method does is to produce what we call a risk curve, or the return value as a function of return period. So you have 10 years, 100 years, 1,000 years here, and it can, with the covariate, you can change the mean essentially of the distribution and produce a fit for 1900 and a fit for today. And today was 2019 in this case, because we looked at the heat waves that occurred in the summer of 2019, record heat waves. So in this case, what these curves tell basically is that between a pre-industrial and today, the observation, this is only observation, tell you that there is basically 2 to 3 degree difference of temperature between the two curves. That's what the fit makes. I mean, with data, it's not an assumption. It's a fit, and it also tells that the event that we had in the build in 2019, which is right here, like 37 degrees, actually, it's probably it has probably gone higher on the days after. But in any case, even for this temperature, it was almost impossible to find such a temperature in pre-industrial conditions, which means that this heat wave actually could not, or almost not, have occurred in the pre-industrial. So with this curve, this is the basis of many works. And we can calculate the intensity change here and the probability change as well by looking at horizontal differences. So here it goes much further. In any case, so this was with observations. And obviously, with observation, we cannot tell what happens. We cannot tell it's climate change. It can be something else. If we want to tell that this is climate change, we have to kind of control the assumptions. This can only be done with models. So the idea here was to repeat this same kind of curves with the models and look at the intensity changes that would be found within the models. So for the observation, it's about 3 degrees. It's what we saw in the previous. And for the models, it's going from 3 degrees for HAGEM and to only 1 degree for other models. So these are a list of models. Some of these models are actually ensembles of models themselves. They are even bias corrected. For CEMIC5, for Eurocordex, they are regional models, global models, regional models again. HAGEM is a different, has a different setup. It has pre-industrial conditions. It has runs with current conditions as well. So basically, all models kind of underestimated the intensity change of heat waves, and that is actually what poses some problems today. I'm going to come back on that. Probability change, it's numbers going from 10 to 10,000, basically, because we are in the very sensitive range of change of models. But basically, this is what the attribution gives. It gives numbers from models, from observations, using extreme value theory in a climate change context. So the nice thing with this was that actually Freddie and Geert Jan wanted really to go further, to push a little bit further and do it in real time, because this is exactly how it makes more impact, because you get a lot of focus on the event when it's real time. So it's not so easy, because then it becomes a little bit, we have to rush on the analysis, and we have to kind of have some guidelines to not go in wrong directions. So this could have been done, this has been done actually with a protocol, which was designed so that we can make the analysis in a kind of systematic way without thinking too much in practice. This is not really true. We have to think each time, and there is discussion about how we define the event, etc., etc. So, but at least there is a protocol for doing the analysis and for presenting results that we can communicate before actually the paper is accepted and peer-reviewed. So the idea was to publish a paper for the protocol and then just apply the protocol. So it's like, you know, a weather forecast, basically. That's and I think Miles' presentation will give another way of doing things like that in a few minutes. So it's an endless list of papers that were published, and I'm just putting the list of what is cited in chapter 11 here from Geert Jan, and only from him and the team that could contribute actually to this figure. So it's an enormous amount of work from Geert Jan and colleagues, and which led to this, to building this figure and ending with the conclusions that we have in the AR6 now. It's enormous. So other questions, and I will. I don't have the time, but yeah. But how much do I have left? Because I will probably. So it's probably like 15 minutes left. Yeah, good. I think Geert Jan has had a sense of what is contained in the observations. That's what struck me most actually. The observation. He had the feeling of the observation, what they tell. And one day we were discussing. One day we were discussing at the canteen in France, where I was working with Pascal Yu also, and he told me it's very strange. you know, we don't see much fog anymore in the belt. So there's a trend. Wow, there's a trend. Is there something to explain? So discussion went on, and we tried to find observations. Here and there, we could find some observations in the UK, and then we fell on a huge database of visibility from the airports. That was a mine of gold. And yeah, we could calculate the trends, actually, from all these stations after some cleaning, because they were not really quality controlled. And on the left-hand side, we could demonstrate, actually, that there is a trend since the 1980s, I think, or 70s, in visibility, in low visibility days. There's less and less low visibility days everywhere in Europe. And actually, so it was really amazing how we discovered this pattern at this time. And we could also look at the impact in terms of temperature. So yeah, so this was one of our first personal collaboration with Geert Jan in 2009. And there were many more later. One of his best questions is, why aren't models working properly? I think that is a question which is still remaining here. And attribution is actually an excellent framework to address this question, to look at extremes, etc. Yeah, models are working approximately properly if we look at global scale, if we average, kind of. But if we look in details, it's not so nice. So one of his best topics was heat waves, and we have a paper. So I'm kind of unveiling the results, but it's probably his first author paper on which was just revision was just sent. There's nothing revolutionary in this paper, but it just says that attribution of heat wave is actually very difficult. We could think that heat waves is simple because it's temperature. You know, temperature is changing, and with global climate change, and then I mean it's quite obvious that we will have some signal in the heat waves. But actually, it's not so obvious because there are many issues with the data, with the other phenomena. For instance, on the left-hand side, this is the observation this is the trends in the observation in stations, mostly in the Northern Hemisphere, where we see a lot of trend, especially in Europe, not so much in the US. So there's already something to explain here. Why do we have this blue pattern in the US? So the blue pattern is actually depending on when we start to calculate the trend, and essentially due to the fact that the record heat waves were obtained in the 1930s in the US, because of, especially in the mid-eastern US, because of what we call the dust bowl phenomenon, which was a use of land which was not very good, and since then, and the ground was a lot removed at this period, and there was huge heat waves. But then after there was irrigation, etc., etc. But another pattern from these two graphs, these two maps, is that CEMIP 5, these are the models, climate models, on average, do not simulate enough trend in the extreme temperatures in Europe. And this is a quite general thing. So if we look at things a little bit differently, on the left-hand side, we have the models, the global models, and the trend in the warmest day of year, calculated from the models and calculated from the observations. And you can see there's a big, all the models are on one side, and the observation is at the end of the model spectrum, which we don't quite understand very well yet. And for regional models, increase in resolution doesn't solve the problem. Sorry, these are here. Doesn't solve the problems. So we are still left with this kind of questions. And if we look at extremes, again, we are looking at this kind of plots that we show before. So these are models, again, with the fit of the parameters for the observation in blue, for the models or the different kind of models in red. And for France, for instance, you can see that all the models are outside the confidence intervals of the observation. They don't match. The models are wrong. They are not wrong, but they are not matching the observations, obviously. So we still don't understand that. They have too much variance, too much variability. That's on the left-hand side. I don't comment on the right. Yeah, if we look at Oxford, it doesn't improve much. A little bit better, but CMIP 5 is really bad. If we compare with the observation of the station, the historical station in Oxford, where is it? It's somewhere around the back. Okay, good. It's nearby or? Yeah, okay. So urbanization? No. Any? No, it's very well. Yeah, anyway. I guess there's a lot of discussions. But anyway, the models don't match very well. Okay, so there's a topic that I like a lot, but I'm not going to speak too much about that. It's basically that we have this problem with models not matching the observations, and we have to understand why. Is it aerosols? Is it feedbacks from the surface processes and things like that? Or is it dynamics? Maybe we don't simulate the right patterns. And I think there's probably a mixture of different causes. And yeah, I'm not going to detail this, but I just wanted to say that there's a lot to understand from the dynamical point of view. I'm not sure the models are simulating the right frequencies of blocking and stuff like that at the moment. And I'm sure they are not really doing that well. So I'm going to skip some of the things and go back to the winds because it's an interesting case. Now we had a storm or two storms actually in 2018, which made a lot of damage, and of course the question of climate change was on the table. And these two storms, Friederike and Eleanor, made a lot of damages, and these are the winds that were observed at the time in kilometer per hour. So it's exceeding 120, 100, even 40 in some places. Yeah, so we looked again at models and observations for winds, calculate the GeV stuff with the maximum wind in the year, and look at the results. So what's so this is the result. So basically, if you look at this at the left storm, which is the Netherlands, actually UK, Netherlands, Germany storm, the observations, what they tell is that we have a decrease actually in the intensity of storms. So this is and frequency for a given intensity, and the models give the opposite. So are windstorms intensity increasing or decreasing? So we don't know because the observations are going in one way and the models are going the other way around. Not much. Actually, we could not solve this issue, and it's still a question, still an open question. Many models, and we always say windstorms are not changing much, but there was a few windstorms recently. You remember that. And yeah, there are questions. There are very important questions from insurance company about clusters of storms. Do clusters increase or not, etc. So we don't know much because again, the observations are telling less and the models are telling more. And we could, so this is unpublished material because we wanted to do a paper with these figures and we could not actually. Yeah, there are many papers like that left to be done. So what he did at this time with a few colleagues from KNMI was to consider what we call the potential wind speed. The potential wind speed is actually the wind speed that would occur in a place at the same place if the surface was flat, basically, no obstacles, nothing. But the anemometers are always at places where there are houses, trees, and stuff like that. And it's usually increasing, urbanizations and the forests are increasing. So in the left figure, we have the real wind speeds that are measured, and the observation. We see that the wind speed is, so the blue is the historical and the red is current. So the wind speeds, the extreme wind speeds are decreasing. And on the right-hand side, it's kind of corrected wind speed with the same roughness assumption. And so this reduces. It's not overturning the result, but it's actually reducing. So we think that roughness changes play a role in the decrease in windstorms. But we don't have the end of the story. Okay, I guess I have only maybe a few minutes, or is that correct? I have to probably finish. There are more complicated events, and I'm not going to detail too much, basically, where we also have problems with models, even with temperature, like we analyzed the April 2021 frost, which was very important for France because we had lots of damages in the wine, so it's important. There we also see pictures with models. So what we see basically is that after bud bursts have come, we have more actually frosts, more lower temperature, because basically the bud burst date is coming earlier now with climate change. But again, the model is not having the same intensity as the observation. So we are working on it. We have EXAIDA, which is H2020 project, in which actually Geert Jan was one of the initiators, also with Dim Carmo in the Netherlands, but we have many discussions with also British colleagues involved in this project. And the idea is to kind of progress in this understanding all these questions that are left open, and try to use also machine learning and AI for detection, causation, and projection of extremes. So just a final word, as I wanted to say, Geert Jan was a real source of inspiration for papers and for projects, actually funded projects now. So it's really interesting, and yeah, it's my pleasure to present. It was my pleasure to present that. Thank you.
I will talk about a slightly different aspect of the work that Robert and I have been doing with Geert Jan, and that's about how we frame the question and also how we talk about it. So I will not talk about meteorology or GV fits or anything like that, but about about the other aspects. And so I think when Geert Jan and I, and also Miles was involved at the time, was starting to think about setting up a project that would rapidly answer the question whether and to what extent climate change played a role in extreme events. The reason for doing that was that the question was asked anyway. The question of was it climate change or not is usually how the question is framed in the public, and someone will answer the question. And it was never a scientist who answered the question, at least not sort of within the first year or two after the event occurring, but it was people who only had political motivations. And so we thought that needs to change, and that was the reason why we started World Weather Attribution, with which Geert Jan and I have led since he passed in October, and which now Robert and I, and together with Sjouki and Sarah in the Netherlands, and Martin van Aalst from the Red Cross, are continuing to lead, and maybe eventually also get some funding for it. But that's a different topic. And so these are just two examples of where where sort of people have made very sweeping assumptions of the role of climate change in extreme weather events. And I will talk a little bit about later that the quote here from the head of the World Food Program, that's actually quite really wrong. And that was the last study that we did with World Weather Attribution, where Geert Jan was still involved. So, and this is sort of in Geert Jan's word, the question we are asking with, so that's a slide that I've stolen from the talk that he has given when explaining what is actually the question that we are asking in World Weather Attribution. And it's, so it's not usually, well, the question is of course asked because something very concrete has happened and led to very concrete damages. But it is actually really, really difficult, and it's one of the hardest parts of the whole attribution to go from damages and from something that has happened in the real world to an event that you can simulate in a meaningful way with a climate model or even observe in weather data. Because of course, you have observations for temperature, usually in daily resolution, sometimes higher than that, but if you have higher resolution, you don't have the models that have higher resolution, so you can't compare the observations with the model, so you can't do the attribution study. And we also usually have just single variables like temperature or rainfall. But of course, what happens in the real world, and you just need to think about a storm, there's a combination of wind speeds and rain intensity, but also just where exactly the rain fell and what the season before happened, what the state of the soil is, and all these things, of course, play a huge role in terms of what the damages are that we observe. When you can't have the exact definition of the event in the attribution study, so you need to find an event that is a definition of an event that is related to the impacts in a way that the event definition you use is actually telling you something about the risk for these impacts now and in the future. But of course, it still needs to be also something that you have observations and you have models for. So there's a trade-off to be made. And how to make this trade-off is what makes attribution studies really hard, and especially what takes a long time in the rapid attribution studies. And so this is also in sort of in Geert Jan's words, the steps in the attribution studies. And Robert has talked about the observational trend analysis and the model analysis. And number 6 is sort of the hazard synthesis, that were the pink bars you've seen in Robert's slides before. And that's the things that you can do kind of automatically, where you have just statistical models, methods that you can apply. But everything else requires quite a lot of expert judgment, and you have to take decisions, you have to make assumptions. And that starts with the analysis trigger. So when do we actually do a study? And you've seen already from Robert's talk that a lot of the event attribution studies are in Europe. And that's, of course, well, we live in Europe. So it's kind of the stuff where we get lots of questions, but most of the other scientists in the world who publish a lot also live in Europe and Northern US. So there's a huge bias towards attribution studies in the global north. And so, yeah, do we just do the events that we find interesting? Do we do the events that the media finds interesting? Do we do events that have a lot of impacts, but how do you measure the impacts? So how do we decide when we do something, especially because World Weather Attribution, while it has not always been not funded at all, it has never been funded in a way that we could just do every extreme weather event that happened. So there's always the need to decide, okay, how do we use the very limited people power that we have available? And then the second bit is how do we define the event? So how do we connect what's happening in the real world with something that you can reasonably expect to have data for or simulate in the model. Then, of course, there's lots of expert judgment on which models you use. So how can we, and there are some aspects of model evaluation that you can automate, but there's still a lot of expert judgment. So, okay, is the seasonal cycle that the model reproduces, is that too bad, or is that just about good enough, or all these kind of questions? And then there is a huge different aspect that in world weather attribution, and particularly at the insistence also of Geert Jan, we have always tried to really make strong and include in the analysis, because what turns weather into a disaster is to a very large degree not driven by the hazard, but by vulnerability and exposure. But unless very, very, very small exemptions, and this is from a drought analysis that we did. I forgot to put the reference in there, but it's from a paper from 2015, where we did an attribution study on a drought in Sao Paulo and found that actually, when you look at the changes in the rainfall, which is the top plot, you see no change. But there were, and the drought was not very extreme in sort of extreme event terms. It was about 1 in a 10-year drought. Similar droughts have happened earlier in the 21st centuries and also in the 70s, with much, much less impacts than, or much, much fewer impacts than the one that was observed in 2014, which we analyzed here. And so the reasons for these large impacts were obviously not in the weather event. They must be somewhere else. And in that case, we have worked with people from Sao Paulo who had access to population, but also to water usage data. And what you can see on this other plot is that on the one hand, the population, which is the red curve, goes up. But when you look at the dark blue curve that sort of almost exponentially picks up in the last 10 years before the event, that's the water usage in the area of Sao Paulo where the drought happened. And so that's why the same kind of drought suddenly had huge impacts on the population that the previous droughts have not had. And so that's an example where we could actually really quantify what the role of changes in exposure and vulnerability were that explained to a large part the disaster. And of course also look at the role of climate change. So that was the kind of study where we thought, okay, we really want to do every attribution study like this now. And then we completely failed to do that. So we almost no other attribution study that since we've done has actually quantitative data on vulnerability and exposure. But of course, that doesn't mean that vulnerability and exposure is not still hugely important. And so that's why we always have, usually in the paper that we write, a long paragraph on vulnerability and exposure, on the role of vulnerability in the events. And also it's always in the key messages. But this is an area where Geert Jan and I always felt we really need to do more work, and we really need to also expand our networks, because we have a great network of climate scientists, meteorologists we work with, but we need more people who can help us, and stronger networks with people who can help us on the vulnerability and exposure side. So this is really something where I think world weather attribution will put a lot of emphasis on, and where we hopefully will improve what we can do in the future. But of course, I will just show briefly 2 examples of the kind of what that means in terms of the types of results that you can get. So this is an example where really climate change played a huge role. It basically made the event possible in the first place. It was the heat wave in Canada and Pacific Northwest last year, where the results were very similar to the plot that Robert has shown earlier, where you do not get this kind of heat without human-induced climate change. So there it's fine that our headlines and our stories are about climate change, because that's really an event that is about climate change. But then the other event that we did last summer, or well, we started last summer, but finished it in December, because it was really difficult, was on the drought in southern Madagascar, where, as I've shown in the very first slide, the head of the director of the UN World Food Programme has said this is the first climate change-induced famine that we have. And when you look at the data, that's just not the case. There is, the drought was an extreme event, so it was a rare event, but it was within the natural variability, and there's no trend in the lack of, or in sort of the failure of rainy seasons in that part of the world. But of course, there's a lot of other stuff going on in the part of the world that really makes any kind of slightly extreme, and that was a very extreme event, a catastrophe for the population, a very highly vulnerable, very poor part of Madagascar, completely dependent on rain-fed agriculture, but then also that the COVID had a huge impact in the area, and also there were large-scale deforestation, which made the impacts of drought much more severe than when forests were still intact. So there were lots of things in terms of vulnerability coming together that turned this drought into a disaster. But climate change was not one of them. And so this is actually the kind of events that we really wanted to do more of, because it's the kind of events where, first of all, there's a lot of misinformation, and also it's a part of the world where we just don't know much about the role of climate change at all. And when you remember the hexagon figures that Robert showed earlier, you've seen that for the droughts, and particularly for the rainfall events, there were a lot of gray hexagons in the global south. And that's all the parts of the world where we just have neither the data nor scientific analysis that show whether there are trends and observations or whether they have anything to do with climate change. So that's a huge gap. And this figure that you see here is also illustrating this gap. So these are deaths associated with extreme events since 2003. So since Miles' paper, so since in theory, event attribution studies could have been done for these kind of events. And then, so the larger the red circle, the more death from extreme events. And it's extreme events for which we in principle could do attribution studies, so heat waves and droughts and heavy rainfall events. And overlaying them in black is the death for which attribution studies have been done. So that doesn't mean that all the black deaths are associated to climate change, but we know what the role of climate change is, or at least we know that we don't know because of some data issues or something. So where these events have been studied. And you can see that in many, many countries, there are entirely red circles, so that for not a single one of the extreme events that have had some impacts on human lives, an attribution study has been done, nor a detection study. So there are huge gaps in our understanding, and that is and sort of based on this, we have designed the trigger criteria for world weather attribution, so that that we do a study, that we are sort of triggered to do a study when a certain number of deaths are associated with extreme events, and particularly in the global south. Quite often, so when an event is triggered, that means that we consider doing an attribution study. And quite often, we then end up not being able to do it because we don't have enough people power, or we don't have can't get any observational data so that we could do a study. So it's still very aspirational, that we would like to really close this gap a little bit, but it's something that we have that especially working with Geert Jan and also Martin van Alst from the Red Cross, we have tried to design the protocol in a way that we would be better able to do these kind of studies. So this is sort of the top end of the attribution study in a way to find out what has actually happened. Why do we do a study? When do we do a study? And how does the weather event interplay with other things that are going on in the world? Another aspect that is hugely important, especially for world weather attribution, and has been especially important for Geert Jan, is sort of why do we actually do this? We do this because people ask the question. And so that means, and it's usually the people are not scientists, but it's people outside of science that ask the question about the role of climate change. So that means we have a responsibility to communicate the scientific results in a way that makes sense outside of the scientific world. And so a lot of, because of that, we have sort of not just designed the scientific protocol, the scientific way of doing the study, but also what do we do to make the communication work? And a really important part of that is that we have to write a scientific paper. Even if we never publish it in a peer-reviewed journal, we have to write the scientific paper first, rapidly, while we do the study, because it's just impossible to communicate even with other scientists exactly what you have done, exactly why you have done it, which assumption you have made if you haven't written it down. So that's something that we learned the very hard way, the very first study, the very first rapid study that Geert Jan and I have done on the Paris heat wave in 2015, where we thought we don't need this, we just write down some facts and do the plots. And then there was no way that we could even check ourselves on each other. So for that, even just for internal purposes, it's crucial to have that that scientific paper, very boring to read for everyone else, so that we know what we did, and that we and that also then the scientific community could redo our study and check the assumptions that we have made. But of course, you don't want to publish a scientific paper on your website and say, "Here, world, go away." So the next part of the communications protocol is that we use that scientific paper, and based on that, write a web summary, which is usually which has like here. So the text here is sort of one of the key points from the web summary, which gives some of the key messages of the paper and a very brief explanation of sort of which variables we've looked at and why, which is sort of usually what we hope that for lay people will be enough to understand what the point of the study is, what the main narrative and the main findings are, and show some humanly understandable plots that give some context to the event. But then, of course, there's then the next bit of the communication that we do is that we write a press release, which we write with our press team, which is all our press work is done for free because they think the work is important by the GSCC, which is a global media company, a bit like the Science Media Center here in the UK, but global, and write a press release that sort of translate the web summary into something. Why should a journalist find this interesting? How is that linked to sort of what has been said in the public about the event before? And of course, some quotes from the scientist. And then we always have done a press briefing, and we have never done a press briefing without Geert Jan, because he spent a huge amount of his time talking to journalists, explaining to journalists in excruciating detail what we did and why we did it. And through that work, that Geert Jan and also I, but every time I speak to a journalist now, they say, oh my God, your colleague Geert Jan, he always spends so much time with me, and making me feel guilty that I've maybe not spent quite as much time with them, but he has really, really led the groundwork there. That we now have a global network of journalists who have reported on world weather attribution in the past, who know what we do, who understand it. And so that actually the reporting in the press is really accurate. And so that you, and this is really just an illustration, so that you get even the nuances of the study right. So it's not the headline, the head of the World Food Program is wrong, but the headline is that poverty is the main driver, but also that climate change, of course, is therefore not irrelevant for Madagascar. So it's a really nuanced sort of way to report on actually our findings, and this is really because they have always, and this is another slide that I've stolen from Geert Jan's presentation a while ago, because a big part of world weather attribution, but in particular Geert Jan, is that journalists have someone to talk to. And usually when extreme weather events happen, there are days or weeks that we don't do anything else but talking to journalists. But sort of that is why we have started to do this, and why, and I think what actually we at least understand as really an important role that we as scientists have, to not just do the science that we find interesting, but also that we sort of then bring it back to the people who ask the question. And I think that was a huge drive of what Geert Jan did, and he did it very well. So we have a lot to live up to that, and I'll leave it at that. Thank you.
And because I knew that Freddie and Robert would be talking about sort of what Geert Jan's great contributions to all this is. I'm talking primarily about something that I think Geert Jan would be interested in. And I'm confident he would have been interested in it, because we were arguing, because he was never very interested in what he'd done. He was always interested in what other people were doing, and explaining in great detail why it was wrong. So I know that he would, I wish he was here to ask the questions in this seminar, because he would have so many questions, but it's up to you now, okay, to channel those questions. I'm going to be talking about a study which I was arguing with Geert Jan about a week before he died, and he gave no hints there was anything wrong with him, but he was sending me long emails explaining to me the fundamental flaws in the study I'm about to describe to you. And in fact, I hadn't actually, Nick Leach, of course, as ever in Oxford, I'm going to be talking about what other people are doing, and most of what I'm talking about here is Nick Leach's doctoral thesis work. And indeed, I was very. We talked to Geert Jan about being a co-supervisor because of COVID and things. That was sort of difficult to set up. He would have been an ideal examiner. So I think we'll have to sort of imagine that exam. Just to sort of take you back to the motivation of all this, the original grumble in that 2003 paper was triggered by hearing on the radio, so I can't remember who it was from the Met Office, hello if anybody's watching from the Met Office, saying the usual mantra, global warming could make this sort of thing more frequent, but it was impossible to attribute this particular event to past emissions of greenhouse gases. And this was a time when our garden was very soggy, and in fact, Dave Frame and Sam Dean's house was underwater. So they often pointed out to me that I started writing articles, based on a soggy flower bed, and they actually were under 2 feet of water. And anyway, this sort of triggered thinking about what we could do about this. And it was, Freddie and Robert were emphasizing the challenges of producing results rapidly. And just to put that in context, it is important to the first sort of major computer-based study of a precipitation event was 11 years from the event of publication, and this was Paul's thesis project, and I think also 6 years from matriculation to publication, but he got there in the end, and he did get the last laugh. But it shows, what it took, and Geert Jan's enormous contribution to this. Robert's already mentioned this study was to show how you could get broadly similar results, indicative results, just from looking at the data, and you could do it so much faster than we were doing these laborious studies with the climate and weather models. But as Freddie's been emphasizing, with limited resources and doing things triggered by the question, you end up with inevitably that selection bias problem that you were pointing out in those hexagon diagrams. There are certain parts of the world don't get studied and so on. And models may help us to address that. And something which we've sort of aspired to do with perfect timing here, right? Hello, Tim. Because Tim had multiple seminars this afternoon to give himself, I think. So that's right. Sorry, I shouldn't have drawn attention to that. You're coming in the back there. But ever since we sort of started talking about this, the aspiration was, can we just get the Met Office to do this, as a service, as part of just, and using the same tools that they use to forecast the weather, tools that increasingly, some argue, are getting close to passing what you might call the model Turing test. If you look at these two figures, which one's the model, which one's the observations. Of course, people who are keen on clouds and convective parameterizations will very quickly point out there are very important differences between these two pictures behind me. You'll notice, for example, in the deep tropics, you've got much stronger convection in one than the other. But which is correct, which is the satellite, which is the model, is not instantly obvious, unless you happen to be a specialist. Well, that is the answer. But the one on the right is the European Centres. Yeah, well done, Aaron. You're patting yourselves on the back. But the one on the right is the 18-kilometer resolution IFS, the European Centres integrated forecasting system that they use for the medium range forecast. And the event I want to talk about and the study I want to talk about was triggered by the same Pacific Northwest heat wave that Freddie's already introduced us to. This is it in the European, in the reanalysis. You can see the extraordinary temperatures they were seeing in that region of British Columbia in the Western US, and then overlaid on this, Nick, all these graphs are from Nick, thanks Nick. All overlaid on this is the geopotential height anomaly, that heat dome that developed over that region over the week of the heat wave. And the crucial question, okay, so we want to study the counterfactual question of, what would have happened without human influence? And we can't do that in the real world because, of course, we don't have a real world without human influence. So how can we find a model that we can be reasonably confident is good enough to simulate the event in order to look at the role of human influence in that model? And so what's good enough? Obviously a wonderful test of whether the model can actually simulate the event is whether it forecasts it. And in this particular event, the European Centre, the IFS system, forecasted extraordinarily well. So that's the event itself, showing you just, over the years, the hottest, the maximum temperature observed. You can see how far it was outside the range of normal variability of maximum temperatures in that region, or in that specific box that's highlighted there, which is you can see the sort of dotted line there highlights a little box there, which was chosen by the Weather at Home team to represent the event in question. That sort of shows what happened over time. That's the event in the analysis. This is what happened and that's the 3-day forecast. So you can see that, you know, it's pretty close to passing a Turing test for the event itself 3 days out. And extraordinarily, well, I mean, maybe those folks at ECMWF would think, yeah, of course we can do this. Well, it is pretty extraordinary, but 7 days out, they were getting, I was trying to take credit there, wasn't I? No, they were getting the model forecast. Still, you know, the depth of the strength of the anticyclone, the heat dome, the surface temperatures, all there. Even 11 days out, they were seeing this was a welter. Almost 2 weeks ahead of the event, it was clearly developing in the forecast. Even in the seasonal forecast, and this is work that Antje Weisheimer led, looking at the seasonal forecasts from 2 months earlier, now looking at the hottest day rather than the temperature at a particular time of the heat wave, there appears to be in the seasonal forecast some indication that we should expect an unusually hot day, although that is an area there is still work going on exactly how we quantify the skill of the seasonal forecast. So the experiment we did, which was kind of ever since, so almost 20 years on, this is kind of the experiment we've been wanting to do, which is why I'm kind of excited about it and was so enjoying arguing with Geert Jan about it, is to take the actual weather model and simulate pre-industrial climate by subtracting both CO2 and modifying the initial conditions of the forecast to simulate a cooler world without the warming due to past greenhouse gases built into the model. We weren't able to do this for the whole thing, but we were able, thanks to the work of Chris Roberts in particular at ECMWF, to do this to the ocean in the model, because Chris had developed a technique for perturbing the ocean conditions so as to produce a balanced state, a balanced but cooler state globally. And what Nick did was to subtract from the ocean temperatures the pattern of surface and subsurface warming, and then correct the salinities to give us the same density field, so that you didn't immediately just trigger sort of massive ocean overturning or, you know, disturbances. So you got a reasonably balanced, revised ocean state with pre-industrial conditions, and then rerun the 50-member ensemble. So this was all done at the ECMWF through a special project, which we're very grateful to the ECMWF, of course, for funding. Just reran the ensemble itself at different lead times to look at the impact of that signal of human influence on the probability of the event. And by the way, we had done this before, and what really frustrates me in not being able to sort of explain all this to Geert Jan, I hope he's listening from somewhere, but because what we had done earlier was a study of the February heatwave in the UK, where all we'd done was modify the CO2. And Geert Jan was thoroughly unimpressed by that study, because he said, well, that's so what? I mean, you just changed the CO2, you know, that's not the main signal. I can tell you, Robert probably wasn't very impressed either, but from that shrug. But I said, yes, but we're sort of getting there. We're trying to get to the point where we're changing the initial conditions as well. And I was just, you know, getting the point of telling him with great excitement last autumn that we, you know, Nick and Antje and Chris had got to the point where we were actually getting closer to the full the full study we wanted to. And by the way, there's another crucial element to this, which is we had to repeat the study, increasing CO2 as well, and adding the pattern which we'd subtracted, so as to check the linearity of the response. And the reason, of course, that's important is illustrated here with a slightly simpler model, the variant of the Lorentz 1963 model that actually Tim suggested in the late 90s as a way of understanding the impact of climate change in a strongly nonlinear system. Thanks to Nick, of course, for these amazing graphics. Blue is with forcing, yellow is without. And you can see the immediate impact of the forcing is to drive the blue trajectories slightly to the right of the yellow ones. And then an extreme event is, you know, the model crossing a threshold here. And you can see that as the ensemble reaches, you know, and this is a case where all of the initial conditions move towards the event. It's highly predictable. This is like the 3-day out forecast, if you like. Everything was going in the same direction, but you see the immediate impact of the forcing driving some of the events to be slightly warmer than others. So you can see the blue with the forcing is displaced slightly to the right of the red of the orange distribution without. And, you know, so you can see the forcing's pretty, the role of the forcing is nice and simple and nice and obvious. Let's take a different case where, you know, starting in a different position, looking for a different event, same forcing, same immediate impact of the forcing. And then as you, in this particular event, the first sort of pass around the butterfly, you don't actually capture many of the extremes. And so you're sort of getting this, and you think, well, it's not really a very interesting result because not much has happened. We actually haven't seen very many extremes in either the ensemble with the forcing or without, but you just have to be a little bit patient and watch that as the trajectories come back into the part of the attractor where trajectories diverge most rapidly, and you'll notice interesting stuff starts to happen. Many more orange lines are turning right as they go into that center, the sort of body of the butterfly, so to speak. And then in the second pass around the lobe, as you know, one lonely trajectory is wandering off to the left, most of them have gone off to the upper right. And now we're starting to see events emerging which actually show rather higher temperatures. And at that longer lead time, you see a distribution of extremes emerging. And now, if you just sort of wait and are patient, you see that the distribution of blue and orange are pretty much identical, despite the fact that the forcing has made the blue events hotter than the orange ones. If you just look at the short-term impact of the forcing, it's also driven many more orange ones up into that upper lobe of the attractor. And that compensates for the impact of the short-term impact of the forcing is compensated for by the change in the probability of that entire regime occurring that results from the forcing itself. So, you know, what we learned from this, apart from that Nick did all this graphics, by the way, in the past 24 hours, which is, I'd just like to sort of flag that. I was saying, well, wouldn't it be good if we did this? And then this is what we got. So well done, Nick. So first of all, the crucial point about a nonlinear system is the response to forcing, and this goes back to, and there's a nice graphic of cups and balls in Tim's paper in 98 or something, illustrating this point. The response to forcing can strongly depend on where you are in the state space of the system. If it's a nonlinear system, a really interesting open question is whether we could understand the differential response to forcing in a system like this by looking at using the actual singular vectors of the tangent linear model to try and see where the system should be expected to be most sensitive to forcing. And the problem is, and this is what has always worried me, particularly about the storyline approach to attribution. I don't know if Ted's watching, but you know, this is for you, Ted. If you work back, you know, if you just look at the sort of short-term forecasts, you can get one answer. Whereas if you trace back through a part of the attractor where the system is particularly sensitive to the forcing, that may drive the answer in a different direction. So how do we address that problem while still using models that we know can actually simulate the event because they forecasted it correctly? And you know, the idea is that we back away from a successfully forecast event until we lose predictability, and this allows us to trace the impact of the forcing versus initial conditions over a range of forecast skills. So here we are. This is back to the Pacific Northwest heat wave case. Familiar return time diagrams that Robert and Freddie have both shown you. This is just at 3 days. Red is future, blue is past. And you can see there's a very consistent displacement towards warmer in the future and cooler in the past, which actually, to be honest with you, even at 3 days, we didn't know quite what to expect because we were kicking this model pretty hard. This is, you're changing CO2 and you're changing all ocean temperatures back towards pre-industrial in one direction and sort of like 50, 60 years into the future. And yet 3 days out, it's still forecast a heat wave. So which, you know, if it, you know, I know the flap of a seagull's wings is supposed to set off a tornado in Texas. Well, not in this model. This heat wave was going to happen, even if, you know, no matter what the seagull did. So even at 7 days, still very clear signal emerging. In fact, the signal gets stronger, the noise gets louder as you move further and further ahead, but the signal is still there. Even at 11 days ahead, we're seeing the impact of human influence consistently emerge, where in the warmer world, we're seeing hotter Pacific Northwest heat waves than the cooler one. And again, just to stress, it didn't have to be so, in the sense that it could have been the case. And as Robert immediately pointed out, but have you looked, you've only looked at one event. And it is true. This is the first event we've looked at with this approach, and there will be others. And of course, it may well, what we don't know is, you know, were we just really lucky with this event? Was this just a particularly robustly forecastable event? Was there something special about it? No matter where we kicked the model, it was still going to generate a heat wave. Even out at 60 days lead time, so there's the seasonal forecast rather than the medium range forecast, we're still seeing this clear evidence of human influence, you know, adding about 2 degrees. That's the 2 degrees here between the pre-industrial and the future. But as Nick was pointing out, if we look at the global signal, we can say that's more or less an estimate of the pre-industrial to present signal today when you account for what we haven't produced, hasn't yet emerged from these studies. So just to sum up, for me, the most exciting part of this really is just a sort of a demonstration that it's possible to simulate the role of human influence in these specific weather events using precisely the modeling tools used for operational forecasting. And there haven't been that many climate studies done with exactly the same model that's used for weather forecasting at the time. We've done a lot of climate studies with out-of-date weather models. I've built my career on climate studies with out-of-date weather models, you know, finally we're using the tools that are current now, which are therefore being validated every day in the weather forecast model, in the weather forecasting centers, and get all that scrutiny on them that are required for the actual sort of operational tools. For this event, and your point is well taken, Robert, we need to look at others. The forecast was really surprisingly robust. And because of that, it allows us to track back through the forecast to trace the evidence for human influence in the evolution of the forecast and relate that to the role of initial conditions and the role of nonlinearities in the evolution of the forecast. And as I say, my great regrets is that I'm confident that if we had got Geert Jan over to examine Nick's thesis, I've no idea what the outcome of the thesis examination would have been, but one thing I can be absolutely for sure is we would have gone to the pub afterwards and we would have had a fascinating discussion in which Geert Jan would have given me at least a decade's worth of work to do before we'd left the pub. And I'm just, it's heartrending that that's not going to happen. But thank you all very much for coming, and thanks very much everybody for joining in online as well to honor Geert Jan's memory. Thank you.
thank you very much to Miles and all the speakers. I would actually invite maybe all speakers to the front because we'll do questions together. And maybe we can kick off with David Marshall. Kindly agreed to moderate the online questions. So we have to learn hybrid question and answer. But maybe we kick off with an online question before we then take a question in the room.
Okay, so thank you for the online questions so far. We have a couple. If there are any more, please do type them in. So the first question is to you, Robert, from Peter Stott, and it's that you've shown a number of examples where models have problems simulating extremes. What do you think Geert Jan's legacy might be in terms of advising when attribution results, which depend on models, can be trusted or not?
Oh, this one is really tough. I think there are different types. I would say my first answer is no, actually. None of the models, none of the cases are fully satisfactory, at least at the moment. We have so many issues that we need to solve. So we talked about the heat and the heat problem. We talked about the location. For instance, you know, the type of work that you were presenting could work. It could work just because it's a heat wave, it's a stable situation. But if we are in a convective environment, I'm not so sure that you would get even a very short-term indication of the response of the answer. So yeah, I think we need to really look at all the type of questions that come from each event types, and see, and we have very different patterns, very different situations in each case. So yeah, I don't see any generic answer for this. Yeah, maybe you want to answer that. Yeah.
Well, I think Geert Jan's answer would probably have been that it's not quite the right question whether we can trust the attribution studies because of the models, because it's not just the models that we use for the attribution. It's also the understanding of the physics, and we also have the observations. And I think when we have both and that fits, then we can trust the attribution results, even though we may be knowing that there are problems with the models. So I think it's not exactly the same thing. And he would also have pointed out that, well, if you don't trust attribution, then never ever look at a projection. So I think that's also really important to keep in mind, that what attribution does, it's really testing the models in a much harder way than we do with anything else that we do with the models, because we bring them together with the observations on real events. Yeah, so I think that to put the broader context.
Fantastic, thank you very much. We'll take a question from the room, from Duncan, and I invite people also to raise their arms. You might have lost that habit, but get back.
Thank you very much for a fascinating series of talks and a nice description of the work of Geert Jan, which I wasn't really aware of. Yeah, thank you. I was fascinated to using operational weather tools now to do the attribution. We didn't say it, but I guess the vision is that potentially we could forecast these extreme events before they happen, and potentially do we do forecast, but attribute the events before they even happen. And what implications might that have for damages and the implications for responsibilities?
We've actually done that. So we've done an attribution. One of the very first attribution studies that we did with World Weather Attribution was to do one based on the forecast rather than a heat wave that has actually emerged. So I think it's a different question, of course, I think if we didn't communicate it very well at the time, I think, because we just said, oh yeah, this is based on the forecast, and then the forecast turned out to be a degree hotter, a degree too cold in one place, and a degree too warm in another place. So the exact numbers, of course, were not the same, which sort of put us off a bit from doing that. But I think your point is actually a really good one, that you could say, well, based on this forecast, you would have, that this is sort of the threshold for really high mortality. You would, that that many less people would have died if it wasn't for climate change. So I think you could actually turn that into a really powerful communication device. But I think it's because, especially for heat waves, the exact numbers are so sensitive to the threshold of how hot the heat wave is. It's also, you make a lot of errors if you do it on the forecast. So I think that it's a bit tricky, but.
Can I just add on this one to you, Freddie? Because I think, yes, for the forecast of weather, but as you mentioned, the impacts are often largely due to exposure and vulnerability, and this is maybe more forecastable, and unfortunately. And is there something we can do with this? I mean, we know that there are some areas in the world, especially now, which are very vulnerable. And so just when we see in the forecast that there will be something, whatever the amplitude, maybe this is also one way to communicate things. I don't know. So this is more forecastable.
Okay. I'll ask another question that was asked online. So this one is from John Methan. It was asked during your talk, Freddie, but I guess anybody could answer this. Is it necessary to do attribution studies on extreme events that are without impact to refine the conclusions from attribution studies on events with major impacts? And I'll just point out the camera online audience is over there, so it might be good to direct the answer.
Well, I don't think, I'm not sure it's necessary, because there are so many extremes that have so many impacts, and for quite a lot of them, there are actually a lot of extreme events that are happening and have impacts that we don't even monitor. So I think if we continue to focus on the ones that are sort of it's a bit windy in the UK, but the impacts are relatively small, I think that is definitely continues to be useful, so that we learn something about the science and understanding of. But I think actually there's so much to do in parts of the world where the impacts are huge, and so much more that we need to understand, and which aspects of the weather actually cause the impacts, because ultimately it's the impacts we care about. That I think there are way too few people who do this kind of stuff. So I'd rather they focus on the things with impacts.
Yeah, I just wanted to add that Geert Jan would have also answered that he always wanted to attribute events that did not occur because of climate change, and like cold spells or things like that. And not sure we did many, don't think so. But also there are some events like cold spells which disappear, which do have impacts also. The disappearance is having impacts because the nature needs cold in the winter in our countries, at least. So yeah, it needs to be repeated, because sometimes you hear on the TV that it's fantastic to have a cup of coffee outside in February in a cafe, but nature doesn't like it very much, actually.
So one of the things I was arguing with Geert Jan about was whether, because one solution when you don't have enough people is to get machines to do it for you, and I was sort of discussing with Geert Jan whether it would ever be possible to replace him with a machine, as it were, and I'm not sure. Well, obviously, the trips to the pub, no. He was pretty confident that the attribution analysis. Well, I don't know. Aspects of the attribution analysis could be eventually sufficiently automated that you could do it by by machine. I know this idea is doing this, and you know, you've got these ideas about using machine learning to automate it. Of course, once we're doing that, then that, you know, levels the playing field. That solves a lot of problems, because then the machines can analyze all the events. Sorry, I've forgotten. I'm answering the audience. I should have been answering the camera, because sorry, John. Okay, but did you want to comment on the? Okay, so there is a paper which both of you are on, or Robert is involved on using machine learning on this. Or not yet.
The whole project is
Yeah.
about it.
Okay, so idea. Yeah. Okay. So okay, there will be papers. Sorry, as you can tell, I'm not involved in this project, so I don't know what's going on. But there we are.
Thanks. I was just wondering, what research would you most like to see done in this area now? Like, if you had a new PhD student, what would you ideally have them do?
Who wants to kick off?
You start.
I want to know whether that supposition about singular vectors is correct. So if you've got a few years ahead of you, maybe, you know, postdoc or PhD student, come on, that's got to be a really meaty problem.
Yeah, I would want PhD student to really extend the framework so that we have vulnerability and exposure properly in it, and not just as an add-on, which then always falls under the table when we talk about it, when people remember about it.
Yeah, that's probably slightly more useful than nerding out over singular vectors, but you know, it depends on what department you're in.
Yeah, well, I still have to read the working group 2 impact chapters, impact attribution of impact chapters. They are not. I still haven't read it in depth, but certainly the impact is, as you Freddie said, an area where we would need to put more strengths and to have more advances in knowledge attributing impacts, because actually the working group 2 actually is not exactly doing it the same way as we did it so far. So we need to kind of put things to bring things together to understand how something that has an impact has to do or not with climate change.
Take a couple of questions from the online audience. So the first is from Fraser Lott to Freddie. I must say you're very popular online, Freddie. Here, I think all the questions, almost all.
We knew that.
So from Fraser, Freddie, how have you, Geert Jan, and the Worldwide Weather Attribution Gang gone about establishing links with local scientists for their expertise and data, especially on the short time scales that you work?
Well, we just, to start with, we were just trying, but first of all, asking in our networks, do you know someone in the Met Office in Madagascar? And I have done quite a few projects with, for example, scientists in India and scientists in Africa. So the likelihood that they did was slightly higher than when you ask in the UK Met Office. And then we tried to snowball from them, and we tried, So I think that's how. So and sometimes if they are asked by someone they know, then they are. People want to know the answer. So people are usually, if they can at all, they are. We have never really experienced that people said, "Oh no, I don't want anything to do with this." It was usually that people say, "I would be very happy to do this." And then in half of the cases, at some point, the head of the Met Office was telling them, "No, actually, you can't do this. So you have to back off." So there would be a lot more authors from local Met Office on our papers if that wouldn't happen half the time. But so yeah, and that from then we tried then of course to keep the relationships going forward and write more science papers. Okay. But it's possible, but not always as easy as you would wish.
Yeah, if I can just add, there's something we started to discuss also in our meetings, but discussion was not going very far so far. I think training, specific training session could be interesting. We have to organize it, which means that at least one person is in charge of making it happen. But I think it could be extremely interesting to have some training at some point. Yeah.
Okay, and then a question again from Rowan Sutton. Important question. So what specific steps would be most useful to close the gaps you highlighted for studies of events in the global south? And to what extent is the lack of long observational records fundamentally limiting?
I think it's not the lack of long observational stations that's fundamentally limiting, because quite often they do exist. They are not existing in the public databases or in the databases that are available, but they exist in the records of the Met Offices. And so people, the local scientists, local Met Office people have it. So I think the biggest bottleneck is that, as I said, well, at half the time we start working with often quite a few people from local Met services, and then they are reminded by their bosses, this is really not your job, don't do it. So that there is very few researchers in the global south are employed to do research. They are mostly employed to provide a service, either seasonal forecasts or teaching. And I think that is the real bottleneck. So I don't know, NERCs and other funding bodies of this work, of this world, if you're listening, that I think is really, really where things need to change to fill this gap, because we can't do this without the local expertise.
I can't resist sort of adding a plug here. Of course, if the one tool that these Met services are all used to using are the global forecast model outputs, because many of them are sort of signed up with the European Centre to use that model output. And therefore, if they're already used to using it, it would make it easy for them to look at counterfactual cases. You know, so for example, Nick will, in the course of his doctorate, probably get around to looking at the Pacific North. He'll get around to looking at, 2% of what's coming out of those simulations. There were global simulations. There's a gold mine in there. And what ideally would happen, we will of course make all the data available, but we make it available to anybody who's interested. And of course, if this was a service going on regularly, you would know. If an event happens where you are and you're interested in what the impact of human influence was on that event, you can go to the European centers, the Copernicus Climate Service Attribution Center, and download the relevant simulations and have a look. Wouldn't that be a good scenario? We're not there yet, but hopefully we'll get there.
Yeah, okay. So Geert Jan, of course, went through attribution and added rigor. It really highlighted the rigor of the outputs there. How do we actually continue that when we start thinking about impact and going above and beyond just attribution of events, but actually the impact of that event maybe on the energy transition, on food supplies? So working with those other communities of researchers, how do we convince them to actually work and research and act with the same level of rigor that Geert Jan brought to attribution as a whole?
That sort of implies they don't use rigor. Yeah, that question sort of implies that the other communities don't apply rigor. I think it's just very different methods. And of course, if you have an impact model, if you have a hydrological model and compared with a different hydrological model, you compare two systematically and sort of from a setup point of view, two completely different things. Whereas if you compare different climate models, they still are based on the same physical equations. And so you can't do exactly the same thing that you do to climate models to impact models. So I think it's more that we have to learn from each other how to still be able to quantify the sampling and the systematic uncertainty. And I don't think that there's unwillingness to do so. I think it's hard to talk to different communities both ways. And obviously Geert Jan was very good at that, but I think that's something that probably other people can also achieve.
Something my advisor told me once upon a time was, if something's worth doing, it's worth doing simple-mindedly, and if it's not worth doing, it's not worth doing well. And I think one of the things we can learn from the, I remember you telling me that, I don't know if it was I don't know if you were quoting somebody else, David, or whether it was something you sort of thought up on the spur of the moment, but I'll give you the credit. Oh, it stuck with me. And I think one of the, so there are, the reason for, I think there's something about the need for us in the climate science community to learn, and simple-mindedly is a compliment here. You know, simplicity is enormously important. And we perhaps have allowed our part of the problem in many cases to become unnecessarily complicated, and pride ourselves in the rigor of what we do, when in fact it's just of what we do, and or the expense and the number of flops that it takes to do what we do. So I do think we have to be quite careful there. And one thing that I think Freddie and Geert Jan, and Freddie in particular, have really helped drive us towards in the attribution area is listening to other people about what the question is, rather than defining the questions ourselves using the tools that we happen to like to use. And I think that's an incredibly important aspect of this interaction with the impacts and the economic communities behind it.
Yeah, I just want to add that maybe rigor. Of course, Geert Jan was rigorous. Many of us are rigorous, but I think what characterizes him is the depth of understanding, especially the observations. If he looked at a time series and there's a break or something like that, he would need to understand where it comes from. And I think this is essential. I mean, the rigor is in the method, but the understanding of exactly, you know, he would have a comment on each CMIP model. I don't dare to say about a few models here, but so it's really understanding what was wrong in this model and what is wrong in this observation data set. And I think it does not, it is not a specificity of our community. I mean, understanding is, that deep understanding is also in social science. So yeah, I think the question has to be put in a different way.
Okay, a question of clarification online for Miles from Dakian Yu. So thanks for your talk. I don't fully understand your backward test of forecast error. Do you mean there are some certain initial errors that will make the prediction fail and other initial errors may not?
So apologies, I was whipping through a study fairly fast, and we weren't really testing the skill of the forecast here at all, although we were impressed at how robust that skill was. That was why I was probably going on about that in the talk. But yes, I mean, in terms of what you're saying about there are certain types of events or certain sequences of events where the forecast might be quite fragile, and if you disturb anything, it just goes away. And there'll be other cases, as Robert pointed out, heat waves or sort of stationary stable systems like a heat dome might be an example of that, where it's particularly robust. Doesn't matter where you kick the model, it still does the same thing. So, you know, distinguishing those will be a matter of I don't think there's another way of doing it other than just doing it, but it would be fascinating to keep the plug going if we could actually use the tools we use for quantifying uncertainty in ensemble forecasts directly, so singular vector analysis, to actually try and predict which sort of situation we might be in using the relationship between the forcing and the singular vectors. But that's sort of speculation at this point.
Okay, thanks. So we're going to take one final question from online before we wrap up and go to drink. So it's from Rowan Sutton, and it's a question for all three of you. Should we worry about the risks of misattribution, for example, when later studies contradict earlier ones?
Of course, we should worry about that, because I think we should make sure that our studies are as robust, as rigorous as we can, so that we make clear how do we define the event, that we evaluate the models in a meaningful way. But I think it's a possibility always in science that that you find with different tools or different models that you find something is not is different. That should not stop us from doing it. I think it should really just spur us to try and really, and that's what we try to do, to be as transparent as possible and to really try to quantify the uncertainties and not say more than we can say. And well, we have most of the rapid studies that we have done, we went back afterwards and have done with them slightly different models, newer data, and send them to peer review. They have always been within the uncertainty of one another. The prose has always dramatically improved in the write-up through the peer review, but the numbers have always been, within the uncertainty of one another, which I think shows that we might be too conservative for many people in the way we do this. But this is exactly why we do it in this way, to really try and find out what are the different types of uncertainty and how what can we say at this point in time and what can we not say.
And my point on this is that unlike forecasts of 2100 temperature, this kind of work, attribution, is falsifiable on the time scale of the career of the scientist making the claims. Which is important, and it puts the heat on. And actually, I think one of I think I was running out of time, but one of the points I wanted to make at the end of my talk is that I think attribution and the rigor demanded for actually getting attribution claims right, and Freddie is, I think, I gather there's a dossier on Freddie in some courtroom somewhere. There's a lot of scrutiny on this stuff. Sorry, was that? Oh, possibly one on me as well. Anyway, there you are. I'd love to see it. But the point is that the scrutiny that this kind of work will get, I think, will ultimately be very healthy for our discipline. It'll force us to use and to test the tools we use as hard as we can, because you can say what you like about the 22nd century, you're not going to be around to be proven wrong. But this sort of work is right at the cutting edge, and that's one of the reasons why I think it should be absolutely central to any package of climate services.
Okay, my point on this. To go to my point on this, I will take the examples of the PNA heat wave. I think I was extremely uncomfortable with this one because we are facing a new type of beast, and we have to be a bit careful. And even Geert Jan was extremely careful in the beginning. We had long discussions on. We have to put the assumptions we make before, because we don't know. It can be contradicted in the future because we are facing different kind of events, and probably in the coming years we will face more events like that. So we have to be extremely careful. And what was done for that was there's a couple of sentences in the paper saying that we assume that this event belongs to the population we know. This is what we assume. So I think the good way of doing things, facing this kind of questions, is just putting in clear the assumptions we make. We are not sure about, we were not sure these assumptions were true, because it could be a different kind of world for this kind of event. We don't know, probably more and more studies are coming saying that this is not the case. It was predictable from models, from your study, and also from other studies like Erich Fischer has done last year. And but we may enter this kind of era where we have new types of things, and we have to be very prudent.